Okay, so go ahead and you are going to vote for when you want in the future, after Monday's date, when you want to actually have homework due and your quiz option due. Oh, just kidding. Okay, so either doing it on, and I didn't leave that option. So doing a Thursday due date, Friday quiz, or Friday due date, quiz on Saturday. Yes?
Will it change when they're available? When the date opens?
The only thing is that the quiz will only be open on that day that it says. So if it's like Saturday, it would be 8 a.m. Saturday morning till midnight Saturday day. So quizzes will only be open one day. Homeworks will be open up to the deadline of, when I say here like Thursday, that would be up to Thursday night. So Thursday night do homework and then quiz Friday. Or Friday, homework due, quiz Saturday. Homework due Saturday, quiz Monday. Or homework due Sunday, quiz Monday. So I'll give you guys a couple minutes to vote. Please give input so you have a voice here as far as how you prefer this. Okay. So very close tie doing Sunday to Monday, but I think it wins out to do, that is so close though. Thursday, keep Thursday date for homework and then Friday for the quiz. I take it you did not vote for that one.
No, I didn't! I don't have time to do it during my weekdays.
Okay.
Oh.
How long is the quiz usually?
So the quiz will be like 2 problems. And so again, a KVL, KCL, expected to take like a half hour to 35 minutes. You'll get 50 minutes to do it in, but everybody that I've seen usually gets done quicker. Okay, so we're gonna keep Thursday due dates for homework, and then Friday will be the quiz. So after Monday, next week will be the odd week because of this delay in getting this posted. So Monday will be the first homework due, and it's actually 2 homeworks. Homework 1 and 2 will be due. One's on KVL, one's on KCL, but it's just 2 problems really. So as long as you're able to do the problem, you won't have to keep iterating and redoing the problem. You can get through it. And then the quiz will be posted on Tuesday. Okay, any questions on that? Okay, you guys ready to get back to what we did last time? Okay, so okay. So last time we talked about multiple things, and so these were the learning objectives that I wanted you to take away from last time. So being able to apply units, meaning milli, micro, pico, understanding those unit notations, and then also you are introduced to amps and ohms and watts and volts, all of those which you probably should have seen from physics if you took physics 2, but I think this requirement is only physics 1, so you may not have seen those. If not, just note that that needs to be familiar to you and that you're going to want to go study those a little bit. Understanding current, understanding voltage, identifying an ordinary node. Anybody want to take a stab at ordinary node definition? What is an ordinary node? Yes?
Node with 1 entrance and 1 exit.
So close, there's a little bit more detail, and it involves elements. And when I talk about an element, it could be a voltage source, it could be a current source, it could be a resistor. So if you were to reword that using element in there, what would it be?
The node is only one element on either side.
Okay, so it's a wire in between two elements would be that ordinary node. Thank you. So you were right, just trying to clarify the wording of it. So extraordinary node is different than an ordinary node, which has two elements with the one wire in between. That is where the node is between the two elements. And an extraordinary node difference is what? Anybody want to take a stab at that one?
Is it more than 2 elements?
There you go. So more than 2 elements. So when I have 3 elements, that's 3 or more elements that are connecting together, all joining in a junction, that's the extraordinary node location. Okay, then we talked about applying KCL, and we went through an example, and now today we're going to talk a little bit about identifying a branch and a loop, and then we're going to talk about KVL, which is Kirchhoff's voltage law. Okay. Okay, Kirchhoff's voltage law is where you have to understand the concepts of a branch and a loop. So a branch is when you have an ordinary node. All of these are ordinary nodes, correct? So look at this. This has an element here and an element here. And there is one wire in between them, and that's what we call the ordinary node. So this is an ordinary node. Over here, this would be an ordinary node. So in this circuit, there are no extraordinary nodes, and therefore it is just one branch. If you have more than, it's down the other way. So we'll look at this one. First off, let's label all of the extraordinary nodes. So take a second to try to identify yourselves. Where are the extraordinary nodes here? Okay, this would be one. And then I am going to highlight the wires until I come to a element to denote that everywhere along that wire it's going to be the same voltage, meaning it's the same location, even though it physically is not because there's a wire connecting them. Okay, where else? Anybody want to speak up to see where another extraordinary node is? Yes.
The V3, V4, V5.
Okay, in between there. So this is another extraordinary node. Thank you. Anyone else?
V2, V5, and V6.
Okay, great. So this one, correct? Anyone else? There's one more.
Is that a 5?
Yeah,
V5, V4, and V6.
yeah. Yes, right here. So we have, this is an extraordinary node. So between two extraordinary nodes is going to be a branch. So that's the definition of a branch, is all of the elements that are between two extraordinary nodes. So branch is so it's all elements between two extraordinary nodes. Okay, then a loop is going to be a pathway from one location back to that location. So you pick a point. It can be anywhere in the circuit. Find a different color here. And, well, I'll go on this one as the example. So say I want to start here. I can either put my pencil down or whatever I'm using to draw. And then I'm going to physically move a pathway, bigger, and go in a path until I reach back to that original position. That is a loop. And the reason why you need to understand what a loop is because when we take a voltage loop, we go through that pathway and we sum up all of the voltages around that pathway, and that equals 0. And that is the law itself for Kirchhoff's voltage law. So this now comes into, we have to understand the voltage difference or the voltage polarity. So here we see that we have a plus and a minus. So we have a plus and a minus here, a plus and a minus, and a plus and a minus. So on your pathway, you're going to take the sign that you reach as you move through the pathway, and you're going to use that to sum up your voltages. So with the currents, we were summing in and out of a node. In was positive, out was negative, or you can do it vice versa. Here we're going to take the same sign that we come to as we go around this loop. So I'm going to go back and I'm going to start my loop again. And this time as I go, once I hit an element, I need to decide which one I'm going to take as far as the polarity. So I like to physically circle these. So I like to take it as I go out of the element, the sign, but you can take the first one. And if you stick with the first sign that you come to and circle that, you circle all of the first ones that you come to as you go around your pathway. If you start with the second sign, you always take that sign that you go through after you've gone through. So if this is plus, this would be minus. And then I come to this one, and again, that's a minus. And then there's no more elements as I complete my loop. So this equation ends up being the plus VDC minus V1, and then a minus V2 equals 0. And that's my summation. Does that make sense? Okay. So now we're going to do that with a little bit more complicated circuit. We've already highlighted all the extraordinary nodes. So now we want to pick where we want to take our pathway. So to write these equations, we need to pick the pathway, and we can start again. It's arbitrary where you start. So I'm just going to pick a point, and randomly I'm picking this location right here. So if I start here, and I am going to also pick which direction do I want to go to. So I can go, this might be easier to see up there. I can go around this, or I could go down, or I could go through V3. And again, arbitrary way of direction of where you want to go. I could start down and go up and around. The only thing that is what you need to make sure you do is wherever you start, you have to get back to that same start point without retracing a different pathway that you've already gone through. So as I go through here, if I go through this, this would be a plus for V2. I go down, and then I can decide, do I want to go left or keep going down? Somebody call out something. Okay. So going left, I reach V5, and I'm going to do a plus. And then, do I want to go down or keep going left?
Down.
Okay. So I decide to go down. So there's my V4. So I do a minus. And then to get back to my pathway, I need to go left. And then this is going to be a plus for V5, and then I'm back at the beginning. So this is going to be my equation. Anybody want to say it out? Thank you. Yep. So plus V5 and then minus V4 equals 0. So correct, that will be, and this is a plus, which is on there. So plus Vs, or you could start with a minus V2 plus V5 minus V4 plus Vs. But just make sure you include all of the elements that you took around the pathway. Okay, let's do one more and then you guys get to try some of this on your own. Okay, so picking another arbitrary path, we're just not going to want to do the same one again. Okay, so we could start at the same place, but notice if we go down and go through the same pathway we just did, it's the same pathway, but just negatives with it, okay? So you want to make sure you're doing unique pathways. So we could go down, and instead of going up through V4, we could go through V6. So that would be a pathway is to go down through Vs, over to V6, and up all the way around V2. Or you can go down, over, up to V5, but note if you come to V5 and you go down here, then that is a closed loop right here, because you can see you've already retraced that pathway. So if I did that, I would need to go up to V5, but continue over to that side. Does that make sense? Okay, so somebody can pick a point. Anybody pick a point. Somebody throw out a point.
Take one. Dead center.
Dead center. Okay. So let's start right here. And you get to choose down, left, right.
Right.
Okay. So we go right. We hit V5, so I'm going to circle the V5. Okay, we can go up or down. Okay, up. Hit V2, so I circle which, plus or minus? Plus, correct. And then I come through here, and I can go down or to the right. Okay. And I'm back to this, and I circle V3. So what will this equation be?
V2 minus V3 minus V5 equals 0.
Okay. And one thing to check on these is like after I've done this is you see you have 3 circles, so you need to make sure you have 3 elements in there. So that's one check that you can kind of do on this. Okay, so now I know like I have 2 equations. I have 3 known values there, V3, V5, V6. So I can write, let's see how many, so I have 1, 2, there's 3, 4. So maybe I'm going to have you guys write 3 more unique equations. Using these voltage loops, and then go ahead and try and solve for Vs, V2, and V4. So you guys can break up into small little groups and start working on this. And then we will talk about the answers. So again, introduce yourselves to your neighbors. You can work on it for a minute by yourselves and then kind of talk to your neighbor and see what they got with it.
That's what I was saying. I'm like, what? That'll be
Yeah.
That becomes an extra. So we're right here. That's
Yeah, that's fine.
Actually, I think. All right, once you get the solution for VS, V2, and V4, go ahead and you can put them in. see if I can. I think I can share. Let's see.
We can't add special characters. We can't put a period for.
Oh, you can't put a period.
You want us to just do like
Multiplying one of them by 10.
Sorry. Had to find. Okay.
I know. I was like, what?
Okay.
Oh,
There we go.
dude, that is so bad. That is actually like. Why?
Okay, I'm gonna try and change the type. I think it will let me change this type. Let's see. I think it was open-ended. Okay, we're gonna move to this one. Let's see. Open-ended. I think on open-ended you can put it. So just put it in the order of VS, V2, and then V4. So put a comment in between them. Seeing if this will let you put in the decimals. Okay, looks like there's a pretty good consensus going on here. I don't see any that are different. So, good job. Okay, so let's talk about this. Okay, different pathways. So you could have a loop in this one in the right corner. You can have a loop in the left corner, and then you can have a loop in the right corner. So this one would be a plus V4 minus V5 minus V6 equals 0. Trying to remember which other ones we did. VS, V2, V5, V4. So then you can do a loop around the whole outside. So plus, minus, and then a minus. So plus VS minus V2 minus V6 equals 0. And then you could make a pathway. Is this a closed path? If I went here, I'm seeing some head shakes. What is wrong with this? It is not. What's wrong? Yep. Correct. So you can't overlap. So this is overlapping as it connects at the left node right between V3 and VS, or V5. I guess it is VS. So this would not be correct, so I couldn't do this one. Let's see. What about this one? There we go. Okay, that one? No, right? Same issue. Okay? So you have to make sure it's just exactly back to the right one. So the only pathway left that I don't think we've covered is this one. We did that one. Or did we do this one already? V2, V3. V2. Wait a minute. 2, 3, 5. Okay. Yeah, we didn't do this one. And I typically go in my loops to my right, but I could go in a pathway from my left around. It doesn't matter which direction you do. You just have to be consistent with what signs am I taking. So as I go through, it's always that second sign. As you see here, that second sign would be the plus, minus, minus, plus, minus, or I want to take the first one I enter into and make sure I consistently take those same polarities. So this one would be plus Vs minus V3 minus V5 minus V6 equals 0. So from these, it looks like you guys don't have any problems with the math. So you can get Vs was 6 volts, 2.8? What was it, 2.8? And what was V4?
3.7.
Thank you. I don't have those written down. Okay. All right, so this is your assignment for this week is one problem of each of these types, the KCL from last time, this KVL this time, and then your quiz will be on these same kind of things. So you'll see a unique circuit, and then you'll just need to solve it for either currents or voltages within there. It is through a Canvas quiz, so usually I ask you to like sum up these values and then round to the nearest whatever place it is. That step is just so that you can get an auto grade from Canvas, and if you did it correctly, then like in this case, you could add those 3 up and it would give you the right number. And so anyway, that's just a little Canvas thing to be able to get you to solve all these and then put it in there. But it should give you an automatic, like, yes, you got it right, or no. So if you got it right, you get 100%. If you didn't, you can submit your work for the quiz and be able to get partial points, and then get some feedback on like maybe what you did wrong so that you can learn from that experience. So that's the goal of the quiz part. And then the assessment, you can just repeat if you don't get the right number, you can repeat it again. I created, like at 2 o'clock this morning, I created some of these problems. So there'll be a database of problems for the homework part. So there might be some errors in there because at 2 o'clock in the morning, I'm a little tired. So if you are like, I'm really confident this is right, I've done it the way we're supposed to, but I just don't see it, please feel free to reach out to me and let me know and I can double check it, okay? But do note, I make errors too. All right, any questions about these topics? Are you guys feeling more comfortable? Not quite as scary, hopefully? So that's what I like to think of. Things look scary in the beginning, but they're actually not too scary. You can always pretty much learn how to do them. Okay, so we already went through the previous learning objectives that we had last time. The learning objectives today is to continue on is to do applying Ohm's law, which is the last law that you need to kind of know. And these are the 3 main, really basic techniques on solving any circuit. So you guys have already made a huge jump from even being able to see a circuit to now like, oh, I can solve some information in a circuit. So Ohm's law, then we're going to calculate power, and then calculating equivalent resistances. So the calculating equivalent resistances is what is necessary to be able to simplify a circuit to solve it in an easier way. So after this section, we're going to start looking at ways to solve circuits a little bit easier. Can we manipulate them a little bit to make it easier to solve? So that's going to be the whole goal of what we do after this. Okay, so we already kind of went through, this was the slide I was looking for. Already defined branch, node, extraordinary node, loop. This would have been an easier circuit to describe those on. Terminology, this is a little bit more complicated circuit, but same things. You have ordinary nodes between 2 elements, and then you have extraordinary nodes when you have more than 2, so 3 or more elements in there. So we have to identify what those are, and then you have different loops and branches. So this is kind of a neat, very simple application. So go back one slide. This circuit here is just a battery with a light. And so this is one way to make a headlight. Very simple circuit, light, add some power to it, and it lights up, just like the lights in the ceiling. This was a challenge though, because this Professor Murphy from Texas A&M had been working on this project, and when 9/11 hit and all of the disaster with that, they needed a safe way to be able to find people and find what was going on. And so they were able to send her robot actually in. But if you remember, there was lots of dust, it was very messy and hard to see. So it was really important for the headlight on this to be bright enough to be able to capture images to send back to see what was kind of going on. And so she was able to send that in there. So started off with a very simple design project of, okay, I need to make this bright enough to be able to see through all this debris. And what was found was that it wasn't very bright with just a battery on it. So an element was added, which was the resistor, and with this, I actually brought a resistor. So a resistor looks like this. So this is a simple LED, which is just a little light. So it is similar to big lights, but just a little version. And then you have these resistors. So a resistor, if you look at it closely, has little bands on it. And each of those tell you information on what is the value of this resistor. So on this, the first band, in this case, which is red, you look over to the resistor color code. They have some nice apps. I don't know if they're working right now, but a couple years ago, they had an app where you could actually just take a picture of the resistor and it would come back and tell you, like, it's this value. But for some reason, they don't always work, and now I think you have to pay for some of them. So if you need to know, there is a chart you can go look up. First band tells you the first digit. The second band tells you the second digit, and the third band is the multiplier. So in this case with red is number 2. So you have a 2, and then the second digit is, in this case, black, which is 0. So it's going to be 20. So that's where this 20 comes from. And then the orange is number 3. And so that's going to be the multiplier of 1,000. So this is going to be 20 times 1,000 for 20K. So this resistor is a 20K ohm resistor. The last band is a tolerance. So tolerance meaning that it's going to be above and below this value. So if you went to measure it, it's not going to be exactly at 20,000. It's going to be within 5% above 20,000 and 5% below 20,000. So if you take the physics lab, anybody here taken the second physics lab? Okay. So you get here's a whole handful of them, go measure them. Did they do that in your lab?
Something like that, yeah.
Yeah. So capacitors, I think at least, they let you, here's a whole bunch, go measure them or compare them to other people's. And you see that there's a range of values. So 19.9 thousand, 20.1 thousand, or 20.1K. So that's what the tolerance means. And there's different values for the tolerances from brown, red, green, blue, purple. The ones that are really small tolerances you'll probably not see, that you're going to just build with because they're more expensive. So if you can imagine, the better tolerance you get, the more expensive they get. So most of ours are going to be the lower tolerances, where you have 5%, usually gold is the majority of them. So they're going to be about 5% tolerant. But there's some silver, and if they have no color at all, you're like, okay, that's pretty variable going on there. All right, so this comes to why the headlight may not have been so bright. So we have to know one more topic, which is Ohm's law. So for Ohm's law, it is a relationship between voltage and current and resistance. So this is one you're going to have to just memorize. So this means that the voltage across an element is equal to the current going through it times its resistance. So if I have a resistor, and I have a current going through here, what is the plus and minus on my current signs? How do I know where to put the plus and the minus?
Plus first and then minus.
Correct? So remember, arrow is negative. So the arrow is where you can remember where the negative side of it is. So with that, you're going to also have the same polarity for your voltage across it. So if the polarities are the same, meaning that my pluses are on the same side and my minuses are on the same side as my voltage, then you're going to have a plus I times R. Okay? So this means that whatever resistance value this is, that voltage there will be that current times the resistance there. If I have a resistor, and again, I draw it the same direction, and I actually have a labeling of voltage going this way. I'll call these 2. Then my V2 is going to equal, these are opposite now, so this is a minus I2 times R2. Okay, does that make sense with the polarity differences? So when the voltage and the current are in different polarities, meaning that on the left and the right is what you're comparing there. If they're opposite, you have a negative of Ohm's law. If they're the same, it's a positive of Ohm's law. Okay. Then we know power is another equation. And power is, again, memorize. So amps and ohms. So unit-wise, I forgot to mention, volts or voltage is in volts. Current is going to be in amps, and resistance is in ohms. So amps times ohms is going to give you a voltage. And then for power, your amps times volts is going to give you watts. And that's going to give you the power. So in this, it's just going to be the current going through the element times that voltage. So in the second one, it's going to be I2 times V2 is going to give you power. Plus and minus for power mean a little bit different than the polarity you're used to. So you either talk about power as being consumed, or producing. So the plus and minus mean a little bit different in power, where you're either, or absorbing, consuming, absorbing would be another term, absorbing. So a battery typically will be producing wattage. So it's going to help generate power. And so you get watts from that. A resistor is typically going to consume the power in it, which makes sense, right? I have a source that's going to produce the power, and I have an element in there that's going to consume the power. And so that's what we're kind of talking about with the plus and minus in power. All right, any questions so far on Ohm's law, power? Okay, so this is one of the issues that why the light wasn't very bright is that there was not enough power being delivered to it. So one way to increase that would be what? How would I increase power? Okay, I could increase current. Is it easy to produce current? How do you produce current in a circuit? Last time video. Somebody say it. Okay, change resistance. That's another way. Bigger battery. That's the easiest, right? I can just add more power by giving it more energy to be able to produce that. So that's the easiest solution. Like, let's just make it a bigger battery. So that was one of the things. Like, you know, but when you're on a robot, then you have more constraints because your size and you're moving, and so you have to consider weight too. So as mechanical engineers, those are other factors you guys have to like consider. Yes.
You like running it in like parallel or in series, like two batteries?
Correct.
So,
Yep. So those would be other things to look at different configurations to see, is there more power in a parallel configuration, and kind of why? Is it because there's more draw of current? So is there more draw of current, they're going to have more power. So yes, those are all great solutions. So with this, I showed you this LED. One thing about an LED is that you end up getting a voltage drop across it when it turns on. So it kind of models a voltage source. So you can actually say, like, if I go across this element, it has some resistance to it that I don't know about internally. And then I can just say, well, I already kind of know there is a voltage drop across it. And this is what this forward voltage of 1.6 means. For a diode, you understand where the polarity is based on the little arrow at the whichever side that arrow is on, or the flat line looks like a negative sign. That's the easiest way to remember where the negative is. Where that flat line is looks like a negative sign, so that's the negative side of it. The way a diode works is that you have to have more voltage on the plus side than the negative side. So I need to put, I don't think I put it on here. I need to put a battery that has, you know, the plus side of 9 volts, the minus side as my reference point. So as long as I have more than 1.6 volt difference between the top and the bottom, that will turn on. The more voltage difference I have on it, more likely it's going to get brighter and brighter. So there's kind of like a minimum. It will start to turn on, but then the more power I can give it, the more brightness it's actually going to have. Okay, so here's a little picture of that robot. All right, we're going to move to now looking at the techniques I mentioned, like how can we make circuits a little bit simpler? Actually, I have time. I'm going to go back up one more. Okay. From here, we're going to use this to actually solve a little bit more information in here. So most of the time, you're going to have like, oh, here's my circuit. How do I find information? How do I find the currents? How do I find the voltages? One, I need to kind of know the voltage across that resistor in order to find how much power is being consumed there. I have to know what current amount is going through the LED to find what power consumption is there. Once I find the current through the LED, I can do I times V and get power out of that. But that means I need to know the current going through this. How do I find that current? So if I don't know by an educated guess of what direction this current is going to go, I can arbitrarily assign it going left or right. I give it a variable name. I use the techniques I know now, KVL, KCL, and now I've put in there Ohm's law, and I can use those to create equations to where I can then solve those sets of equations. So just like you've done in other solutions of other classes, it's how do I get those sets of equations to then be able to solve them? So, educated guess, anyone want to take an educated guess? What way is the current flowing here? Okay, and why? That is correct.
LEDs are direction.
Well, LED's a hint there, but physically, do you guys remember the video from yesterday or Tuesday? What happens when you put the battery on and then you put the negative and the positive side of the little balls? Do you remember that? It makes that current flow in that direction. So it's pushing out from that negative and positive to create the current flow. So it goes out of the plus side and goes back to the negative side. So that was the conventional current directions. So that's why it is flowing in this direction, is it's coming out of that positive terminal, going back to the negative side. Okay, so how many branches do I have here? Don't know? So what do we do to find out how many branches I have here? So unsure, it's looking like a lot of unsure, I don't know. So first step would be to label all the nodes and determine if they're extraordinary or ordinary. So that's kind of going to be your first step in solving any circuit problem, is kind of label my nodes. Identify where your nodes are, label them, and then see is it ordinary or extraordinary. So where's my nodes here? I have a node between every element, correct? So I'm going to have one here, I'm going to have one here, and I'm going to have one on the bottom. So I have 3 nodes here. Now it's like what kind? So green one, ordinary or extraordinary? Ordinary. The red one, ordinary. Blue one, ordinary. So they're all ordinary. So, how many branches do I have? What is a branch first? No branches, correct? There's just one. There's only this one pathway. So when I have extraordinary nodes, I can have multiple branches. When I don't, I can only have one branch. So just the one pathway is my only option in this. I can choose which direction I go in that pathway, but there's only one pathway here. So that means if I have all ordinary nodes, if this is I1, what is the current flowing here? It's still going to be I1, right? What about the bend in the wire? What happens? Same or different current? Same current, correct? Going around another corner? Same current, correct? Just going through the wire in another bend? Same or different current? Same. So it only changes once I hit an extraordinary node. And then after the extraordinary nodes, those currents are going to be different. So this is all I1 throughout this whole branch. So now I can pick, do I want to go clockwise or counterclockwise direction? Somebody tell me. Shout it out. One of.
Clockwise.
Okay, clockwise. So we'll go clockwise. I'm going to stay here and we're going to go up. This would be a plus. And then what is the polarity on this one? So current goes through here. So where's my plus and minus?
Arrowhead, right?
Correct. Minus is the arrowhead. So this one is going to be a minus. And then we're going to go through and plus or minus for the LED. Minus. Okay. So plus V naught. I'm just going to label this Vx. And then plus Vx. Or sorry, minus Vx. And then minus 1.6 equals 0. And Vx, what else do we know using the new equation I told you about? Vx is equal to I times R, so what is I in this case?
I1.
Thank you, I1, and R is 13. So I take Ix times 13, and Ix is my unknown value. So V naught was given here, so VF. Oh, it's asking for the minimum V naught required to turn on the LED. So we want the current to be at least 20 milliamps. And so if we already know Ix in this case and say a minimum of 20 milliamps, then we can solve this for V naught. V naught minimum has to be at least 20 milli times 13 plus 1.6 volts. So that would be our minimum V naught, but most of the time we want a buffer, so we would design it to be as great as we can depending on the mechanical constraints we have with the size and the weight of it. Okay? All right, questions about, so you guys have solved your first circuit. So that is a full solution of here's all the unknowns and now find all the known, or all information from it. Okay, so next technique is to combine elements as much as we can to reduce them down to a simpler connection. So we're going to just talk about resistors first, and there's going to be two terms, series and parallel. So we have to first identify what is a series connection and what is a parallel connection. So a series connection is when we've colored our nodes. I'll use the example down here. Okay, so let's first identify all of the nodes and identify are they ordinary or extraordinary. So take a second to highlight each of the nodes here and then identify are they ordinary or extraordinary. So this will be one. And do you see how you have to draw all of that because the wire connects the top to the bottom? This one connects here. And then I have the last one at the top here. Okay, so what is red, ordinary or extraordinary node? Okay, so it's an extraordinary node. And the bottom might be a little confusing because you don't have anything connected to A and B. So when you're talking about finding equivalent resistances, you're going to treat A and B as if they are elements. Okay? So treat these as if they are elements. Meaning that A then, well, B is a better example. So if B is an element, that makes the blue wire extraordinary, right? If B was just floating and not an element, it would be an ordinary connection because there's only the 6 ohms connected to the 6 ohms. So it's important that you take that extra step to realize like B is actually going to be like my element. I'm going to connect that to some other element. I'm just treating it in the moment as an unknown element, okay? So A and B have unknown elements there. And so once I determine if these are extraordinary or ordinary, I then am gonna see if they're in series or parallel. So a series connection, I'm gonna move back to this. Once you have color coded, the series connections are gonna be your ordinary nodes. And by the way, this is the cookbook that's on your Canvas page. This is the cookbook for nodes, series, and parallel. So on this, an ordinary node, you're gonna have a series connection. So it's ordinary gives you series connection. Extraordinary, if the same colors on the top and the bottom, will give you a parallel configuration. So this is an easy one. R14 and R15, you can see on the right it's yellow, on the left it's green. So on the right side of it, same color, and on the left side of the same color. So R14 and R15 are considered in parallel with each other. Let's see. Here we have R10 and R7 have an ordinary connection between them. And so those would be in series together. There we go. All right, so these two are in series. So this would be a series connection. And these two have just a separation by an ordinary node, so those two are going to be in series. So in series, it's very simple. You can just add them together. So if I was to redraw this, my new circuit is going to look like this. And so this is going to be R6, this will be V2, and this is going to be R10 plus R7. And this element, I should draw it a little bit bigger, R8 plus R9. So now if I color code them, well, I'm going to end up with the same. As I go through this, I see that they're all blue on the top and the bottom. That means that they have the same connection on the top and the bottom. And when you have the same connection, there can be no voltage difference, right? It's just like having a wire. So this is called a short. So the wire on that right side is shorting all of these resistors, and it's going to blow up your battery. So not a good thing to do. It's going to blow up your battery because you have basically connected wire from the positive to the right to the wire of the negative, and as you saw in that video, you're gonna burn it up. So don't do this. Never do this, please. Theoretically, it just means that you've shorted the connection. So you're going to blow up your battery. Not a good thing to do. With this, a short means that your voltage across all of those elements will be 0. So even though there's a voltage source, you're going to blow it up. So it will be dead. So short means that you have the same connection on the top and the bottom of an element. And there can be no voltage difference across them. Get this one. There we go. All right, we're going to look at this example. So in this example, do you see any series connections? Okay, correct. So there's one series connection. Correct. So R5 and R2. So I treat those as one connection, and I notice that R1 has green on the top, blue on the bottom. We also have V1, green on top, blue on the bottom. So V1 is considered in parallel to R1, and then lumping those two branches into one resistance, I have green on the top and blue on the bottom also. So those branches combined give me parallel form. So if I was to write from this point to this point, I would say that R1 is in parallel with R5 plus R2 combined, which is in series, and that's in parallel with R4 plus R3. And then all of those are in parallel to V1. All right, does that make sense? Okay, you guys ready to try one? Yes. Okay. So actually we'll go back up to this one. Okay, so what do you do with the 2 ohm in this when it has a short across it, right? It's got the same on the top and the same on the bottom. You can just ignore it. So with it, you can just kind of scribble it out and ignore. And then with that, you see that you have, what's going on with the 2 6 ohms?
Parallel.
Okay. So take a minute, try and figure out if I was to do what I just kind of did with the other one and find the actual value for the R equivalent here. You're going to start with the A location and then determine, do I have between the 1 ohm and then the next ones, what connections do I have, and try and solve that. The form for the equivalence is for parallel, you take 1 over the value of each one over itself. So 1 over R1 plus 1 over plus R2. So take a minute, try and figure out this R equivalent value. Okay, so quick answer. So we said these two are going to be in parallel. So we're gonna create that parallel form first. What is this value equivalent gonna be? Correct, 1/1/6 plus 1/6. If you have equal resistors in parallel, it's always gonna be half of the value. So if you don't wanna calculate it, you can look at it and say, well, they're equal, it's gonna be exactly half. So this is gonna be 3 ohms. And so how do you get the full equivalence? Correct. One, it's in, now that you've combined those into one element, you just have an ordinary connection, and so you just add them in series. So 1 plus 3 equals 4 ohms. So ULB has some self-test options, so you can do some more practice with these. If you refresh the page, you can come up with some of these for more practice on these equivalent circuits too. And also for voltage and current, KVL and KCL problems too. All right. All right, have a good weekend and see you guys on Tuesday.